when you look at our cytosine, our arabinoside, this is a position number 1 where our pyrimidine joins. So that is cytosine. That's our cytosine. It joins at that position. The way it joins is position number 2. So this is the position number 2. And this position, it joins, of course, at position number 1. These are position number 2. And at position number 2, under normal circumstances, in the ribose sugar, this hydroxyl group is on this side here. It will be coming out like that, and the hydroxyl group will be here. Just like this one. So you can see now that there is that a change of orientation of the hydroxyl group, and that change of orientation is what is making the cytosine arabinoside epimer, and therefore making it now an antimetabolite. So again, it can be changed to the monophosphate. As we have said, it can be changed to the diphosphate, changed into triphosphate, and once that is changed into the triphosphate, then once taken up by the DNA, it will block the synthesis to block the continued elongation of the DNA. Of course, also, it can also be changed to the cytidilic acid, and that cytidilic acid, an excess of that cytidilic acid, or when you have that, in other words, this triphosphate, there is a change of cytidilic acid, the 2-deoxycytidilic acid. This, once it's taken up by this enzyme, which is usually the ribonucleotide reductase. So this triphosphate, remember, it has a fluoro group. So definitely it's an antimetabolite. Under normal circumstances, the cytidilic acid is and this is catalyzed by the ribonucleotide reductase. Then if you have this triphosphate, if it's taken up by this enzyme in place of the cytidilic acid, it will block that conversion. So again, I repeat, this triphosphate, which has a fluoro group, once taken up by the reductase enzyme, instead of being converted to the 2-deoxycytidilic acid, it will block that enzyme, and therefore it cannot be converted into the deoxycytidilic acid. And once you do not again have the deoxycytidilic acid, you require the deoxycytidilic acid to be converted to the to be used in the elongation of the DNA. So once you do not form the 2-deoxycytidilic acid, then there will be no DNA synthesis. And once, of course, you do not have DNA synthesis, then it means the cell will not be able to replicate. The cell will not be able to replicate. Again, do remember, as we had said earlier, this also can be incorporated into the DNA itself. So please differentiate those two mechanisms of action. There's one mechanism of action where the antimetabolite is taken up by the enzyme, because the enzyme is not able to differentiate the true metabolite from the antimetabolite. So it's taken up by the enzyme. The minute it's taken up by the enzyme is stopped. Or occasionally, the antimetabolite could be incorporated into the DNA. Once it is incorporated into the DNA, it does not allow for elongation of the DNA. There is termination of the DNA elongation, and therefore those two mechanisms of actions are very important in blockade of the elongation of the DNA or synthesis of the DNA, and hence, of course, once you do not have DNA and synthesis, for sure, you will not have replication. Another drug, one of the disadvantages of this drug, the cytosine arabinoside, is that it can be acted on by the deaminase enzyme. And once it is undergoes deamination, you lose activity. So they synthesized another drug that was resistant to the deaminase enzyme. So we are saying this drug here, the cyclocytidine or ancitabine, the drug ancitabine is just a structural modification of cytarabine, and the only need for that of cytosine arabinoside was to block the deamination so that the drug has a longer duration of activity. So we are saying deaminase deaminases cause resistance towards cytosine arabinoside. New analogs of cytarabine, which is of course also cytosine arabinoside, or the ABAC, is cyclocytidine. So cyclocytidine was just a structural analog of cytosine arabinoside to stop the deamination, or to block or this drug, the cyclocytidine, was resistant to deamination, and therefore it would have a long duration of activity. Hello? Yes. I didn't see it, but I'm in class now. Can we talk after 11? Okay. So we are therefore saying new analogs of cytarabine, cyclocytidine, were synthesized. Resistance to deamination by deaminases leads to better therapeutic index. The drug will have better activity because it will also have a longer duration of activity. It is not metabolized. So we are saying when you have the cytosine arabinoside, there is deamination or removal of that amino group to give us the uridine arabinoside. You see, when you remove that, you get you change it from cytosine to uridine. And of course, this drug was found to be inactive. So this one now is just, you can see it's a slight change here. We are calling it cyclo because you can't see position 2. The 2-hydroxyl group. This was a 2-hydroxyl group which was here. This 2-hydroxyl group, which is epimeric, still epimeric, is joined to position number 2. To position number 2. 1, 2, 3, 4, 5, 6. Yeah, to position number 2 of the cytosine. And once it's joined there, of course, the cytosine is also, of course, structurally modified. So it's not really a cytosine. So it is this epimeric hydroxyl group joined at that position number 2. You have that ring here. So sorry. It's like you have 3 rings. You have that ring there. That is our first ring. Then you have also this ring here in the middle. Yeah, that ring. And you have now our arabinosugar. So you can see, so you have that one as one of the rings. So it doesn't look very crowded. You have that here, the sugar as one of the ring. And then you have this other ring you have created there by making the cyclic ring there, and you have that ring. So that's why we have, because it is now cyclic, and the reason why we are calling it cyclocytidine. Of course, the cytidine also, the structure is a little bit different. You can see here, you have a double bond. You have a double bond there. Of course, that's not the structure of cytosine. But for ease of naming, then we call it cyclocytidine. And the advantage of this drug is that it does not undergo deamination, and it still has good activity. It can still be converted into 5. It can still be converted. It can still have activity. It can still have activity, and it cannot undergo deamination, and therefore it will have a longer duration of activity. It can still be converted to the triphosphate triphosphate derivatives and the deoxy derivatives, but it is not readily deaminated, and hence it has have a longer duration of activity, as we have said. Then, so that's there is still another class of drugs. So those were still additional pyrimidine derivatives. So there is still another class of drugs which we have mentioned briefly. We want now to put it in its right category. So we have also drugs that are inhibitors of the biosynthesis of the 2' deoxyribonucleotides by ribonucleotide reductase. In other words, inhibitors of this enzyme, ribonucleotide reductase enzyme, ribonucleotide reductase enzyme. And remember, in fact, we had mentioned some of the drugs before. So we are saying for you to synthesize the DNA, the ribose sugar must be converted to a deoxy. If you block that enzyme, the enzyme that is responsible for converting the ribose to the deoxy, is the ribonucleotide reductase. If you block that enzyme, again, you will not synthesize DNA. So the biosynthesis of the 2' deoxyribonucleotides, which are the immediate precursors of DNA, involves the replacement of the 2' hydroxyl group by 2 hydrogens, or by a hydrogen atom. This reaction takes place on the ribonucleotide 5' diphosphate. So for the reductase enzyme to occur, the base must be converted first to the diphosphate, must converted to the diphosphate. In other words, there must be a ribose, and then the ribose is phosphorylated twice. It has 2 phosphates. So that it is this time you don't use a UMP, you do not use the triphosphate. You do not use the monophosphate. You do not use a triphosphate. You use the diphosphate, and it is catalyzed by the enzyme you are saying, the RNA NR, also known as a nucleotide diphosphate reductase. So this is just another name, nucleoside. When now you call it nucleoside, you must mention the others, nucleoside diphosphate, because it's a nucleoside. The nucleoside considers the base and the ribose sugar. But now you've mentioned the diphosphate, then now again it's complete. Or the easier name is just to call it ribonucleotide, because nucleoside diphosphate is a ribonucleotide reductase. So all we are saying is that you have your ribonucleoside monophosphate, and it's a ribonucleoside because you can't see. So it's a ribonucleoside monophosphate. Should be a ribonucleoside. Oh yeah, sorry, yeah, it's correct. Ribonucleoside, because they are saying monophosphate. That's why they are calling it ribonucleoside, because they are the monophosphate. They are bringing it separately. They could call it just it's a ribonucleotide. It's a ribonucleotide. So there you have our base, we have our sugar, and our one phosphate. So it's a ribonucleoside monophosphate. This is a ribonucleoside diphosphate, because if you call it ribonucleotide diphosphate, it means it has 4 phosphates. So it's a ribonucleotide. We have 2 phosphates there. We have 1 phosphate, and then now the ribonucleotide diphosphate is the one which is reduced, and you can see the difference is here, there, and here. So here it is a deoxy because it loses its hydroxyl group. What is important is first to remember that your base must first be converted into to a diphosphonucleotide, whereby it has 2 phosphates, and then the enzyme now acts on the diphosphate to reduce it to the deoxyribonucleoside. So if you have any drug that blocks at that point, it means you will not get your deoxy. You will have your 2 phosphates, you will have the base, but it will not be the deoxy. Once again, you do not have the deoxy, as we have said, then it means you will not be able to synthesize your DNA. Some of the inhibitors of the ribonucleotide reductase, we are saying it is responsible for the conversion, as we have already said, of ribonucleotide diphosphate to deoxyribonucleotide diphosphate. The enzyme contains an ion cofactor, which is crucial to the reaction mechanism. This involves, I don't think that is very important. One of the drugs that we can use is what we call hydroxycarbamide or hydroxyurea. Hydroxycarbamide or hydroxyurea is a clinical useful agent which inhibits the enzyme by destabilizing the ion center. So that is one of the compounds, or I just want us to see the structure. So you can see this hydroxycarbamide. So for hydroxycarbamide, it is just like this is the structure of urea. And then you put this hydroxy group. That's why we are saying it's the same structure. It's the same drug known as hydroxyurea or hydroxycarbamide or hydroxyurea. You have put a hydroxy group there. And we are saying that drug directly inhibits the ribonucleotide reductase. And once it directly inhibits the ribonucleotide reductase, it means you will not form the deoxy, because you see this is a critical point there. This point there will not be changed to that. And this can only be used in synthesis of RNA and not DNA. So that is important for us to note. Another drug we have is gemcitabine. Gemcitabine is a very important drug used in management of pancreatic cancer. It is a result of fluorination of the 2' position. Again, I have given the structure here of gemcitabine. If I make it big, the problem is I have to go back. I don't know whether you can see this small structure of mine here, but kindly note at position number 2. This is our position number 1, where the pyrimidine joins. Remember all these, we are still on pyrimidine analogs. So this is our position 1, where the pyrimidine joins. This is our position 2. And at position 2, all we have done is fluorinated. So that's why we are saying it is a result of fluorination of the 2' position of the sugar moiety. So 2 fluoro groups. It is the 2,2-difluoro. 2-difluoro, position 2, that's 2 fluoro, and then it will be deoxy because it does not have the hydrogens, the hydroxyl group there. So it's 2,2-difluoro deoxy, and this is definitely cytosine. This base here is cytosine, and because so that's why we are calling it cytidine. So it is 2,2-difluoro deoxycytidine, and again it will be metabolized. That's what we are calling anabolism, catabolism. It will be metabolized to the diphosphate and triphosphate metabolites, and it inhibits again the ribonucleotide reductase. So at the diphosphate, it will also compete with 2' deoxycytidine triphosphate for incorporation into DNA. So just as we had said for all the others, they normally inhibit the enzyme, but they can also be erroneously taken up by the enzyme, incorporated into the DNA, and once incorporated into the DNA, then the DNA synthesis will be terminated, or it will stop there. It is used with cisplatin for the locally advanced metastatic adenocarcinoma of the pancreas. So it's a very, very, there's a one time I was dispensing it to a good friend of mine, and ultimately, finally, they passed on. Because once you get this cancer, some of them, just palliative treatment. I mean, of course, it's difficult for some of them, especially when they become metastatic. It's very difficult for them to be cured, but at least you try the best you can to prolong the life of that person as much as you can. And of course, again, as we said, the major problem with these drugs is that on their own, again, they also have their own adverse drug reactions, and you can see that this one will cause myelosuppression, teratogenicity, rhinotoxicity. So they are also not very safe. And that is our structure of our gemcitabine. So again, as you can see, this is cytosine. You can see that. And again, this is the ribose sugar. But of course, it is a deoxyribose sugar because you have replaced the 2 hydrogens with fluoro. That's why we are calling it difluoro deoxycytidine, difluorodeoxycytidine. And we also have another one, which again is structurally similar to gemcitabine, tezacitabine. Again, if you look at these also structurally similar, is that now instead of the difluoro group, you have a fluoro. You have a fluoromethylene group at that position. You have a fluoroalkene group, methylene group at that position in place of the 2 fluoro groups. And again, it has been found to be a drug that also will act like gemcitabine. So I think that those were the last ones in that category of fast. They are pyrimidine, of course, they are pyrimidine analogs. Please do remember all the ones you have been looking at are pyrimidine analogs, but they can have different mechanisms of action in terms of the actual enzyme that they block. But do remember, almost all of them, we have a common mechanism whereby, because they are anti-metabolites, they can be incorporated in the DNA or the RNA, depending on which one you're looking at, can be incorporated in the DNA or the RNA. And once they're incorporated, because they lack the groups that we require for continuity of the synthesis, those groups where you require continuity of the enzyme, the continuity of the synthesis of the DNA or RNA either have been changed. Then since those groups which are needed for continuity are absent or changed, then once they're incorporated in the RNA or DNA, you stop the synthesis of the DNA. And of course, even that DNA is already fraudulent in that it has a member which is not the correct member. So that is one very common mechanism of action of all these drugs. But of course, they also have a specific mechanism of action where some of them go for specific ends. We have talked about those ones which will go for the reductase enzyme. So they will go for specific enzymes, and they can block those specific enzymes. And once they block those specific enzymes, remember, why are they being able to block those specific enzymes? They are taken up by those enzymes. But because they are different from the real metabolite, they cannot be changed. When they bind those enzymes, they block the enzymes. Blocking the enzyme or inhibiting the enzyme, they bind the enzyme more strongly. They have a higher affinity for the enzyme. They prevent the normal metabolite from binding, and they are binding a little bit more strongly, and they cannot be converted into the necessary metabolite. So please note the specific mechanism of action of those drugs, and of course also the general mechanism of action whereby ultimately they will block the DNA synthesis. So those are all some of the pyrimidines. I might not have covered all of them, but at least those are representative enough. Then we have I think I need to make this smaller. Then we have the purine analogs. Of course, we have mentioned, for you to synthesize the DNAs, the RNA, you require both the pyrimidines and the purines. So each of them is very, very important. So we can note that if we look at the purines, we are talking about adenine and guanine. Adenine and guanine. And if you do a structural modification, like where you replace one of the group, one of the oxo group, one of the carbon different. And for some of the drugs, that's what we have done, has been done for some of the purine analogs or purine antagonists. So we can say isosteric thiol or sulfhydro group is replaced with a group to replace the 6-hydroxyl group of hypoxanthine and guanine. What is the difference between hypoxanthine and guanine? What's the difference between hypoxanthine and guanine? What's the difference between hypoxanthine? At least one simple question. What's the difference between hypoxanthine and guanine, class? What's the difference between hypoxanthine and guanine? What's the difference between hypoxanthine and guanine? I know you take so long because you must be checking the answers in your phones, because all of you have internet anyway. So we are saying that at position 6 of this molecules, either guanine or hypoxanthine, you have a carbonyl group. You replace that carbonyl group with a sulfur group. If you replace with a sulfur group, then the resultant drug is a thiol something. So once you replace that hydroxyl group, then now you have an antimetabolite. Like you have 6-mercaptopurine is the thiol analog of hypoxanthine. 6-mercaptopurine is the thiol analog of hypoxanthine. And you find that, I'm just removing my sweater. This purine requires bioactivation to its ribonucleotide. As we have said, they will not just, these drugs usually must be activated to their ribonucleotide, and the name of the ribonucleotide is C6L inosinate or 6-mercaptopurine monophosphate. So it is activated the 6-thioinosate, which is also known as the 6-mercaptopurine monophosphate by the enzyme hypoxanthine guanine phosphoribosyl transferase. Hypoxanthine guanine phosphoribosyl transferase. So that is converting this thio to the phosphorylated. So it is converting it, the thio, to the phosphorylated, again for purposes of activity. The resulting nucleotide is a potent inhibitor of amido phosphoribosyl transferase. So the resultant compound you get when the 6-mercaptopurine is activated to its nucleotide, it is highly potent against, or a very potent inhibitor of amidophosphoribosyl transferase. This enzyme, amidophosphoribosyl transferase, is required as it's one of the basic enzymes you require in the synthesis of the purines. So once this 6-mercaptopurine is activated, it inhibits this enzyme, but you stop synthesis of purines. The amidophosphoribosyl transferase catalyzes another step in the basic purine biosynthesis, the conversion of 5-phosphoribosyl pyrophosphate into 5-phosphoribosyl amine. And the 5-phosphoribosyl amine is one of the precursors in the synthesis of purines. The ribose diphosphate and triphosphates of 6-mercaptopurine are active enzyme inhibitors, and the triphosphate can also be incorporated, the same way we have said, into DNA and RNA to inhibit chain elongation. So the diphosphate, triphosphates are enzyme inhibitors. We have talked about the amidophosphoribosyl transferase enzyme. They will block those enzymes. And also the triphosphates can also be incorporated. Once incorporated, then the chain elongation, DNA or RNA chain elongation. 6-mercaptopurine appears to be related to the inhibition of the purine synthesis by blockade of this enzyme, which we have talked about, the amidophosphoribosyl transferase. This is where we are, phosphoribosyl pyrophosphate. So these are phosphoribosyl pyrophosphate. This is the ribosyl. We are starting, that is a phosphor. This is a ribosyl, and then pyrophosphate is that one. Phosphoribosyl pyrophosphate. So that is what we are starting with. And we have the amidotransferase, which uses a cofactor pyrophosphate. So phosphoribosyl pyrophosphate amidotransferase, and all it is doing, it is converting the glutamine, changes to glutamic acid through, so glutamine to glutamic acid through loss of an amino group. So it loses an amino group, and that amino group is what is added here at this position here. So you lose your pyrophosphate from this position number 2, position number 1 of the ribose sugar loses the pyrophosphate, and you get an amino group. And the phosphoribosyl amine is one of the precursors, one of the basic molecules that you require in the synthesis of the purines. One of the basic molecules you require in the synthesis of the purines. So the minute you block this enzyme, the phosphoribosyl pyrophosphate amidotransferase, you can see it is being blocked by 6-mercaptopurine. Once it is blocked by that enzyme, by that drug, then for sure you will have a problem. You will not make your purines. Once you don't make your purines, then you definitely will not make your DNAs. So these are some of the drugs which we are considering, but we are just looking at this one, 6-mercaptopurine. As you can see, we are saying it has, at that position, it has a thio group. Then you also have the 6, should be thioguanine, not thio, I believe it should be thioguanine. And thioguanine, you see, also has that sulfur group at that position. So guanine has a double bond there and an amino group there. Then guanine triphosphate is just when it is phosphorylated. Again, it has that. And of course, once it is like this, it's what we are saying. It can be taken up. It can be taken up in the synthesis of the DNA or RNA. And if that happens, then definitely you will have a problem. I think these ones are the same. I don't know why I drew them the same. So you have 6-mercaptopurine. Again, this just showing how this drug is working. So we have this 6-mercaptopurine. And it can be converted by the hypoxanthine guanine phosphoribosyl transferase. So this can be converted by the hypoxanthine guanine phosphoribosyl transferase. And you can see it still has our SH there, so it's still a thio. All that has happened is that it has been added on the ribosyl group, which is there. You can see this is a ribosyl group and a phosphate to give us a 6-mercaptopurine monophosphate. And this is what we have said we block. That is what, of course, we have said will block the enzyme. And then also it can be converted, it can also be changed. Here, this is just methylated. This is a way of metabolism. This is metabolism where it undergoes methylation. That one we have mentioned by inactivated to active 6 of that, and inactivated by xanthine oxidase and thiopurine methyl transferase. So this is thiopurine methyl transferase. This enzyme here, thiopurine methyl transferase, and it's the methyl transferase. So this is the thiopurine, mercaptopurine or thiopurine, and we are only saying it can be methylated. Once it is methylated here by thiopurine methyl transferase, then it loses activity. So this on this side, it is the metabolism of 6-mercaptopurine. So it can undergo metabolism through methylation of the thio group to the thiomethyl group, loses activity, or it can undergo oxidation by xanthine oxidase. Can undergo oxidation by xanthine oxidase. It undergoes oxidation by xanthine oxidase. Then at this position here, you can see that position, it acquires a hydroxyl group. So indeed, xanthine is where you have an oxo group there and an oxo group there. That's xanthine. Hypoxanthine is when you have a hydroxyl group at that position. So for xanthine, there's a hydroxyl group there and a hydroxyl group there. And once you have the 6-mercaptopurine acted on by the xanthine oxidase, you can see the changes that occur. So it looks like it's being acted. I would have expected that this is not there. I expected this to be SH. Doesn't make sense to have the CH3 here. So this will be CH, but at this point, you can see it has a hydroxyl group, and also at this point here, which is in the position number 6, 7, 8, 9. This position number 7, 8. At position number 8, it also has undergone oxidation. And now when you have a an oxo group there, an oxo group there, an oxo group there, I believe that is uric acid. Uric acid is when you have oxo group there, an oxo group there, and an oxo group there. That is uric acid. So we are calling this thiouric acid because this group, this position here, has a thio group. So it's thiouric acid. And here you have a hydroxyl group, and there you have a metabolite of 6-mercaptopurine. When this happens again, this drug will not have any activity and it is removed from the body. So we are looking at 6-mercaptopurine. We have said it can be converted to the active anti-metabolite, not metabolite, but anti-metabolite hypoxanthine by hypoxanthine guanine phosphoribosyltransferase transferase, and it is converted to the 6-mercaptopurine monophosphate, and this is what will give us its activity. It can also be oxidized. It can be another metabolites into the methyl thiol derivative by thiopurine methyltransferase, or by xanthine oxidase to give us the thiuric acid. And once it is metabolized into this, then it leaves the body and no activity. Once, of course, it is changed into the 6-mercaptopurine monophosphate, then that, of course, is what is giving us activity. We're also saying, if you look at this point here, that in the body, inosinic acid actually is also a starting point for the synthesis of the purines. Inosinic acid is a starting point for the synthesis of the purines. And you can see inosinic acid again is when you have only inosinic acid. And see, inosinic acid, you have only one oxo group there. Oxo group there. Remember, adenine has an amino group there. Guanine has an oxo group there and an oxo group there. So inosinic acid has only one oxo group at that position, number 6. So inosinic acid, through 2 steps, which we might look at, can be converted to adenylic acid. We are calling it inosinic acid because it has a ribose, so it is a nucleotide. Inosinic acid it's like also adenylic acid, also guanylic acid, cytosilic acid. All those are nucleotides. So inosinic acid, which of course has a ribose and also has a phosphate, can undergo 2 steps to be converted to adenylic acid. So all again we are saying is that this drug can block that change of inosinic acid to adenylic acid. Again, if you don't get adenylic acid, for sure you will block DNA synthesis. So this is what we are saying here. We have the reaction of inosinic acid. So inosinic acid reacts with aspartate. And once it does that, it gives us adenyl succinic acid, and then adenyl succinic acid loses fumaric acid to give us adenylic acid. Those are the 2 steps we're talking about. That inosinic acid, in 2 steps, it can be converted into adenylic acid. So in 2 steps. But we are saying that the thioinosinate, and of course, thioinosinate is where so you can see we had thiouuric acid. So thioinosinate can, I believe that thioinosinate can be able also, this is a derivative of mercaptopuric acid. The thioinosinate is a derivative of mercaptopuric acid. It can again be able to block this step here and that step there. And once it does that again, you will find that you will not synthesize your adenylic acid again. Without adenylic acid, you will not synthesize your DNA. This is the metabolism of 6-mercaptopurine. As we have said, 6-mercaptopurine, it can undergo oxidation by xanthine oxidase to give us 6-thioxanthine. You can see the thioxanthine, you add that group there. So if it was xanthine, it would have a double bond there, an oxo group there and an oxo group there. That would be xanthine. But now it's thioxanthine because of that S. And then again, it can undergo further oxidation to give us the 6-thiuric acid, as we had said, an oxo group there, an oxo group there. This, of course, do not have activity. That also does not have activity. I think we have looked at all that. So we have said also the 6-mercaptopurine blocks conversion of inosinic acid to adenylic acid, and of course, as we have said, therefore, bringing us inhibition. We have also said, I'm just seeing that we have done all of them. We have also said it also blocks the amidotransferase. It blocks the amidotransferase also. So you can see that, and then we've also done its metabolism. Now, so if you look at this drug, this 6-mercaptopurine, the minute it undergoes metabolism, then it ceases to have activity. Just as we looked at when we were looking at the pyrimidine. Sometimes if you can be able to block the metabolism, then you can have the drug to have a longer duration of action. So 6-mercaptopurine is basically metabolized to 6-thiouric acid. You can give the 6-mercaptopurine together with allopurinol. So this is the structure of allopurinol. If you look at the structure of allopurinol, you can see there is a shift of this NH group. This NH group is usually at this position. That NH group is usually at that position within the purines, within xanthines, because this is so it is usually here. This group is usually here. Now, what within inosinic acid, because this is a structure of inosinic acid. So this NH is usually here. So now you have shifted it again to deceive your enzyme, and now they are adjacent to each other. 2 nitrogens are adjacent to each other. So you can see this is a structure of inosinic acid. It has the 1 oxygen there, but the NH has been shifted so that the 2 nitrogens are adjacent to each other. So it is an antimetabolite. But the advantage of this antimetabolite does not really have direct activity. What it does is that it blocks the metabolism of 6-mercaptopurine into the thiouric acid. So it blocks the metabolism of 6-mercaptopurine into thiouric acid, and therefore giving this drug a longer duration of activity. That's why we are saying it's an adjuvant to chemotherapy, because it prevents uric acid formation and kidney toxicity because of the release of purines from destroyed cancer. So we are saying it is an adjuvant because it helps, it prolongs the activity, of 6-mercaptopurine by blocking this antioxidase, and therefore the 6-mercaptopurine is not metabolized into the thiouric acid. We also have another drug, azathioprine. Look at the structure of azathioprine. Again, you can see this is just a purine. Here, it's just the structure of a purine. Just any ordinary purine, because it does not have anything. So that's the structure of purine. And then you add another group, add position 6 of that purine. We can even take it all around. At that position, you add the this group there. You add a tricyclic. You can see there, you add a heterocyclic ring, a heterocyclic thioderivative there. So again, making that compound very, very different. So we are saying it's a heterocyclic derivative of 6-mercaptopurine, azathioprine, designed to protect it from catabolic degradation, not significantly better. So this one is again supposed to protect the 6-mercaptopurine from degradation, but it has not been found to be of any important or to be of any significant advantage over 6-mercaptopurine, not significant better antitumor activity than 6-mercaptopurine. So it is a heterocyclic derivative of 6-mercaptopurine, as azathioprine is designed to protect it from catabolic degradation. So it is a derivative of 6-mercaptopurine. It does not undergo metabolism by xanthine oxidase. So it should have activity for a longer time, but it has not been found to have any better advantage, and mainly used as an immunosuppressant. So kindly note as we have always done, always said, that you try to modify drugs to give you whatever advantage it is. This, the halopurinol, we have said, it is an inhibitor of xanthine oxidase. So therefore, prolongs the activity of 6-mercaptopurine. Azathioprine is a derivative or an analog of, again, 6-mercaptopurine, not itself metabolized by xanthine oxidase. So it should have a better activity, although practically, because of perhaps other challenges, it has been found not to be of any significant advantage. Any questions so far? Again, this very similar. The other one was 6-mercaptopurine. This is thioguanine, so very similar. Again, thioguanine, this 6-thioguanine. And again, it will be converted by hypoxanthine guanine phosphorybosyltransferase transferase into its nucleotide. The same thing we said about 6-mercaptopurine, same enzyme, hypoxanthine guanine phosphorybosyltransferase transferase, was converting it into its nucleotide. And then this, again, can be further phosphorylated into the diphosphate, further phosphorylated the triphosphate, which is the active species which inhibits the enzyme. So that will inhibit the enzyme again and stop the synthesis of the DNA. So the guanine is also incorporated into RNA, and its deoxymetabolite is incorporated into DNA, and it can be used in acute leukemia. Again, this will stop the synthesis of the DNAs and indeed also the RNA. That is the first category of the drugs that can be used. Drugs that can be used to block some of the very, very basic enzymes, or the aminophosphorybosyltransferase transferase, which is an enzyme you require for the synthesis of the amine, phosphorybosylate amine, and that amine you do require it for the synthesis of the purines. So once you do not form that basic molecule, for sure you will not be able to form your purines. Once you do not form purines, they are basic requirement. They are building blocks in the DNAs, so that if you do not have them, then you will not be able to make your DNA. If you don't make DNA, then that cell cannot replicate, it cannot divide, because it requires to form very rapidly. Remember, the DNA, which is a double helix, will first of all separate, and one of the strands will act as a template for the synthesis of the DNAs for the new cell. And therefore, and remember we did say that the cancer cells divide very fast, very, very, very fast, so they require a lot of DNA, and therefore once you do not make the DNAs, then the cells will die. The disadvantage is that as you kill the cancer cells, there is a very high likelihood that you will also kill the normal cells, and no wonder the very, very high toxicity. The other category of drugs, we just have a few minutes, are the inhibitors of the DNA polymerase. Again, you have done all these things, and you know DNA polymerase is very important. It's the one which you now bring up all the building blocks together. All the building blocks you require for the synthesis of the DNA, they'll be brought together for you to synthesize your DNA. So the DNA polymerase catalyzes the synthesis of DNA using the 4 deoxyribonucleotide building blocks like deoxy-ATP, deoxy-GTP, deoxy-CTP, and deoxy-TTP. So these are the 4: ATP, GTP, CTP, and TTP. Those, remember, we do say for DNA you require thiamine, not uracil. And that's why we said if you have any drug that blocks the synthesis of the thymidine, the thymidine, then you have a problem. And of course, that's why we were mentioning the drugs like methotrexate, the drugs like 5-FU, and so on. The anti-cancer drug cytarabine is an analog of 2'-deoxycytidine and acts as a prodrug. It is phosphorylated in cells to the corresponding triphosphate. We had mentioned that arabinosal cytosine triphosphate, which acts as a competitive inhibitor. In addition, can act as a substrate for DNA. Remember, we did mention this earlier as an inhibitor in another inhibitor of DNA polymerase and become incorporated in the growing DNA chain. So it has several ways of activity. It's not restricted to one. It can even block more than one enzyme, as we are realizing. So this cytarabine can also block the DNA polymerase and also become incorporated in the growing DNA chain. This can lead to chain termination or prevent replication of the modified DNA. So it just terminates and you cannot, there's no replication. Also gemcitabine, again, these are drugs we have mentioned. But these ones, of course, we mentioned them under, these ones we mentioned them under, I don't know why I've come back to them, because we mentioned the gemcitabine and also cytarabine, we mentioned them under pyrimidines. So perhaps it's just a comparison or just reminding ourselves that we do have pyrimidines that have similar activity. So the purine analog, the purine, but of course what we are saying is that if this can lead, so this in addition, arabinoscytosine can act as a substrate for DNA polymerase, because now we are interested in the DNA polymerase and become incorporated in the growing DNA chain. So this, of course, these are not, this cytosine is not, of course, a purine analog, a pyrimidine analog. And I think the DNA polymerase, I'm looking at both purine and pyrimidine analog. So I think I've not mentioned that. So I brought it in there. But of course, as we continue doing our notes, we continue modifying. So we are saying, therefore, these enzymes, both this enzyme will inhibit the DNA polymerase. Once you inhibit the DNA polymerase, you will, of course, have blocked the continuity of the DNA synthesis, and definitely you will block the replication. The purine analog, fludarabine, is also metabolized to triphosphate and has the same mechanism of action as cytarabine. So under this category for purines, this is the most important. But it's also good to note these ones, I will definitely put them under pyrimidines. It too also inhibits transcription and can be incorporated in the DNA. So under the purines here, fludarabine is the most important, but under the pyrimidines, which block DNA polymerase, we are saying we have gemcitabine, and we also have cytarabine, which we have already mentioned previously. And all we are saying, this we had mentioned, of course, we are saying it is definitely a pyrimidine derivative. Gemcitabine, of course, we had also mentioned it is a pyrimidine derivative, but the correct one now under that purine class is, of course, fludarabine. You look at fludarabine, it has at this position, it has a fluorine and an amino group at that position. It has an amino group at that position, and at this position, it has a fluorine. So fludarabine is, as we look at the structure, is, of course, a purine. It is a purine derivative. Remember, adenine has an amino group there. Guanine has an oxo group there and an amino group there. So a slight change in the arrangement of those groups. And this now acts as an antimetabolite. Once it is taken up by the enzyme, the DNA polymerase, it will inhibit it. Or if it is taken up and it synthesizes the triphosphate, and the triphosphate with the fludarabine now is incorporated into the DNA, then the DNA cannot continue being synthesized. So it will block the DNA polymerase, and it will also stop the elongation of the DNA, just as we have previously stated. So it's important for us to note that. Then, so that is fludarabine. We also have another purine analog, which we call vidarabine. The names are very close, and this is adenine arabinoside. So again, if you look at this, remember we did mention the arabinoside is where you have at this position here, at position number 2, you have the pimeric hydroxyl group. I hope you can remember that. That's when we were looking at the arabinocyte. It is that here becoming a epimeric, and once it becomes a epimeric, the whole group, the whole molecule changes. You can see this is adenine. It has an amino group at position number 6, does not have any group at that, or has hydrogen at that position. So that is adenine. And the difference, of course, between this is adenine arabinocyte, and adenine itself is the ribose sugar with epimerization at position 2'. So again, this we had mentioned, it's a competitive inhibitor of DNA polymerase, limited use due to its susceptibility again. Remember, this we had also mentioned, because of this amino group. Because of that amino group, that drug can undergo deamination, and this is replaced with a carbonyl group. And once it's replaced with the carbonyl group, the resultant drug will not have any activity. So again, that will shorten the activity of vidarabine. So vidarabine will have shorter activity because of the it can undergo deamination catalyzed by the deaminase enzyme. Vidarabine is an analog of adenosine. The D-ribose replaced by D-arabinose. It is a stereoisomer of adenosine, which we have already said. Whether I'm a bit to finish. It's only now this one. Then here we have another one, cladribine. You can see they are very, very close in their names, cladribine. Then if you look at this is, it's again a purine analog. It's a purine analog, which of course here it has an amino group at that position and a chloro group at that position. So a bit different, because you normally have an oxo group and amino group at that position. So again, this drug here, very, very close to the purines, and that's why we are calling them purine analogs. You can see now introduction of a chloro group, not a fluoro group, but a chloro group. This is the first thing drug we have seen is a chloro group. The others we were looking at, they were having the fluoro group. If again you look at it, you can see that the position number 2' is a deoxy position. It lacks the hydroxyl group. So the hydroxyl group has been replaced with a hydrogen. So we can have cytidine kinase. So, these kinases look like they are not very, very specific. Very specific, because you can see this is a purine derivative. Cytidine, of course, cytidine is a pyrimidine, but it is a cytidine kinase which will convert this, the triphosphate, and of course, once it's converted to the triphosphate, it inhibits the enzyme required for DNA repair, which of course is the polymerase enzyme. So that again, so that is a cladribine, again a purine analog with a slight structural differences, and it inhibits the enzyme. It inhibits the enzyme adenosine deaminase, yielding increased cellular levels of deoxy adenosine and deoxy adenosine triphosphate, 2-chloro, 2' deoxy resistant to deaminase used to treat hair disease. All we are saying is that this drug also, it has one advantage. Remember when we talked about the deaminase, which can be able to remove the amino group. We are saying the cladribine is resistant to the adenosine, or it is not metabolized by the adenosine deaminase. Indeed, it inhibits that enzyme, not metabolized by the deaminase enzyme. It inhibits that enzyme. What would happen if you inhibit the adenosine deaminase enzyme? If you inhibit the adenosine deaminase enzyme, it means there will be an increased level of the triphosphates. There will be an increased level of the triphosphates. And it has been found that if you have an increased level of the triphosphates, whereby they are not undergoing deamination, there is what we call the negative feedback mechanism. We have learned of the negative feedback mechanism. So if you have very high levels of this triphosphate, because they are not undergoing deamination and then being removed from the body, they are not undergoing deamination and being removed from the body, what happens is that high level of the triphosphate becomes a trigger for negative feedback mechanism, and the process stops. The synthesis of the triphosphate stops, and that, of course, again, will bring a block in the synthesis of the DNA. So it inhibits the enzyme adenosine deaminase, yielding increased levels of the deoxyadenosine and deoxyadenosine triphosphate. And with that, these ones also will trigger the negative feedback mechanism. And once they trigger the negative feedback mechanism, then it means that, again, the synthesis of DNA will be interfered with. It is resistant to deaminase, and it is used to treat hairy cell leukemia. This also is another drug, pentostatin. It is also used to block adenosine deaminase. As I have said, once you block adenosine deaminase, it means that there will be an increase in the triphosphates of these bases. And once there is an increase of those triphosphates, the negative mechanism again will kick in, and therefore you will stop synthesizing that. But we will look at it more, because I think we went there. We look at it more when we look at inhibitors of adenosine deaminase. We mentioned that a little bit more in details. But obviously, I'm reminding you is about the negative feedback mechanism. Remember, the negative feedback mechanism is dependent on the concentration of the product. Once you have the product going high because of the fact that it is not undergoing metabolism, then it triggers the synthesis of that compound because of the negative feedback mechanism. And once you have the negative feedback mechanism, then you stop the synthesis. You stop the synthesis of the building blocks. And once you stop the synthesis of the building blocks, then again you will block the DNA synthesis. This happens because of this enzyme. When you give an enzyme that inhibits the adenosine, that is an inhibitor of the adenosine deaminase. Once you inhibit the adenosine deaminase, the precursors do not undergo deamination, and hence, again, as I have said, the negative feedback mechanism will be very, very, very important. So because you can see, like this one, it has a limited use because it will be broken down. So you try to look for a drug that will not be broken down. But once it's not being broken down by the adenosine deaminase, remember the adenosine deaminase is working also on other triphosphates. So it will also block the degradation of the adenosine triphosphate. And once it blocks the metabolism of adenosine triphosphate, there will be increased concentration of the adenosine triphosphate, and a negative feedback mechanism will set in. I think we will get up to there. We have gone. So next time we will finalize on the adenosine deaminase inhibitors. And actually, that is the only little bit we have left. Then we move on to the antibiotics, the anticancer antibiotics. So kindly keep reading these things. As I have noted, the names are very close names, but slight difference in their mode of action. The drugs names are very similar, but they have differences in their mode of actions. Of course, to note is that some are purine antimetabolites, others are pyrimidine antimetabolites, but ultimately, because both purines and the pyrimidines are required in the overall ultimate synthesis of the DNA and RNA, when if you lack either of them, then the process will not go on. And therefore, if you lack any of those metabolites, you stop the process. As we have said, because of the structural similarities between these antimetabolites and the actual endogenous metabolites, that structural similarity is able to deceive the enzyme, and the enzyme can take the antimetabolite in place of the metabolite. In taking the antimetabolite, it gets inhibited. Once it is inhibited, you inhibit that process, and therefore you will inhibit can end up there. It's now actually 11 because I don't want to introduce anything new. 45 of you. I don't know whether everybody is there. Is there any question? I'd asked you initially, has anybody answered? I'd asked about leucovorin. Anybody answered it? Bad. I didn't discuss it because I'd asked you last time about leucovorin. So after this, we will be discussing. I need your assignment because I have not discussed alkylating agents because I'm waiting for your assignment. So after we finish off, there are only two slides left. Then we go into the anti-tumor antibiotics. Kindly draw the structures of the anti-tumor antibiotics. Classify the anti-tumor antibiotics. And then once you classify, draw their structures. Yes, they do have quite complex structures, but try and draw their structures so that now when we come next time, you'll be able to finish quickly. So you still have not answered my question on the leucovorin. Nobody has an answer on the leucovorin. And sign in. Perhaps you'll give me the answer next time, or I bring it in the cart. Perhaps you will have read it. Can you sign in then?